señales, estadística, inteligencia artificial. Para mayor información, los invitamos a que visiten el sitio web del taller.
Work of modern relations between basic sciences and engineering, we are pleased to invite you to the first workshop of mathematics applied to engineering, which will take place at the Research Center for Engineering and Applied Sciences, State of Morelos, on June 27, 2023. The main goals of this workshop are to bring together and enhance the bond between mathematics and engineering communities and to analyze the current development and future challenges of applied mathematics. Original panel processing. For more information, visit the workshop website linked below. Within the framework of modern relations between basic sciences and engineering, we are pleased to invite you to the first workshop of mathematics applied to engineering, which will take place at the Research Center for Engineering and Applied Sciences of the Autonomous University of the State of Morelos on June 27, 2023. The main goals of this workshop are to bring together mathematics and to analyze the current development and future challenges.
The solutions to this model are positively invariant and attractive in a region omega. According to this theorem, we deduce that the theorem is biologically feasible and well posed mathematically in omega. Next sections, basic reproductions number. There are two equilibrium points corresponding to this model, which are disease equilibrium point and endemic equilibrium point. We know that to find basic reproductions number, we use disease equilibrium point. Now, we know that basic reproductions number is defined as the effective number of secondary cases produced by single typical infections in a completely susceptible populations. Here, F contains the entries corresponding to transmission events where an epidemiological birth occurs, and V contains all other changes of state, including death. Here we calculate the next generation matrix A B inverse corresponding to disease equilibrium point. Then we derive the eigenvalues of this matrix and we choose the largest dominant eigenvalues, which is called the basic reproductions number. Next section is local stability at disease and endemic equilibrium point. Here we put the statement boldly if equilibrium point is locally asymptotically stable if r not less than 1, otherwise it is unstable. First of all, here we compute the Jacobian matrix corresponding to disease equilibrium point. Here we observe that 4 characteristic eigenvalues are negative, remaining 2 eigenvalues lies in these quadratic equations in lambda. Here we calculate these equations. We observe that if r not less than 1, all characteristic values of this matrix are negative and apply Rao-Hartree criterion, and we prove that the disease equilibrium point is locally asymptotically stable if r not less than 1, otherwise it is unstable. Next section is local stability at endemic equilibrium point. Since all parameters in this model are non-negative, so it is easily verified that L1 strictly greater 0 and L4 less than 0. Furthermore, L3 greater 0 or less than 0 when r not greater 1. Thus, the number of possible positive real roots of this polynomial g of lambda is equal to 0 can have depends on the signs of L2 and L3. Here we apply Descartes' rule of signs on this cubic equation, and we list the various possibilities for the roots of this cubic equations in this table. From the various possibilities enumerated in this table, we have the result. The system has unique endemic equilibrium if r not greater 1 and cases 2, 3, 4 are satisfied. The system could have more than one endemic equilibrium point if r not greater 1 and cases 1 is satisfied. Similarly, The system has unique endemic equilibrium point if unknown less than 1 and cases 2, 3, 4 are satisfied, and could have more than one endemic equilibrium point if unknown less than 1 and cases 3 is satisfied. Next sections, bifurcations analysis. From the qualitative analysis of this model, we observe that there exist two equilibrium points. One is disease equilibrium point and other is endemic equilibrium point. If unknown less than 1, the disease equilibrium point is stable. Otherwise, it is unstable. That is for unknown greater 1. On the other hand, the endemic equilibrium point is stable if unknown greater 1 and unstable if unknown less than 1 under some situations. As a result, the equilibrium points swap their stability around the point unknown equal to 1. This is known as transcritical bifurcations, and the point of bifurcations is unknown equal to 1. Since the endemic equilibrium is stable above, the point of bifurcations is called a forward transcritical bifurcations. Next section, optimal control of Buruli ulcer model. In these sections, the optimal control interventions for effective management of the Buruli ulcers infections are presented. In order to minimize the transmissions of Buruli ulcers infections in the human populations, we have incorporated 3 types of control interventions into the system. Preventions of disease transmissions using protective clothes and teaching health education, insecticide spray to kill the water bugs, and reducing water contaminations by reducing the level of arsenic in water. From different references, the technique is basically adopted to formulate the objective functions J for the Buruli ulcers model to investigate the optimal level of effort required to control the Buruli ulcers infections. Here, we introduce 3 control measures, namely environmental and health education on use of protective clothing by humans, U1T, use of insecticides control against water bugs, U2T, and use of water purifications control, U3T. Thus, the objective functions is given by Ju equal to 0 to Tf. This, where Tf is the final time and the coefficients beyond V2, V3, C1, C2, C3 are positive weights to balance the factors. Our aim is to minimize the number of infected humans IH, the total populations of water bugs NW, and contaminated water ROI, while we keep controlling cost U1, U2, U3 at a minimal level. As a result, we seek the best control U1, U2, U3 such that G of U1 star, U2 star, U3 star equal to minimize of U1, U2, U3 equal to this set, where capital U is the set of measurable functions defined from 0 to Tf onto 0 to 1. The necessary conditions that an optimal control must satisfy were derived from Pontryagin's maximum principle. The current results for optimal control have been derived from the adjoint variables of the state variables, which satisfy the following set of differential equations. This principle converts system into a problem of minimizing pointwise a Hamiltonian H with respect to the controls U1, U2, U3. The Hamiltonian H is defined by equal to this, where lambda is SH, lambda H, lambda H, lambda SW, lambda IW, lambda ROI are the adjoint variables with total human populations NH and total vector populations NW. Next section is optimal control of Buruli ulcers model. Here we put the statement let U1 star, U2 star, U3 star be the control and all state variables SH, IH, SW, IW, and ROI be the solutions of the optimal control problem of equations 4 and 5 that minimize G of U1, U2, U3 over U. Then there exist adjoint variables lambda SH to lambda ROI that satisfy d lambda dt equal to minus del H by del I, where the value of optimal control U1 star, U2 star, U3 star equal to this. Next section, numerical analysis. We consider the following 3 strategies with 3 controls. Intervention strategy 1, health education and use of protective clothing only. Intervention strategy 2, use of insecticide spray only. And intervention strategy 3, reductions of water contaminations only. Solutions when none of the control measures are implemented, that is U1, U2, U3 equal to 0. In this strategy, the cost for health education and use of protective cloth U1 use of insecticides U2 and reductions of water contaminations U3 are fixed at 0 at the time of simulations of optimal control system. From figure 3a to 3a, we observe that the situations when no control strategy is implemented to the dynamical system, the susceptible humans and susceptible water bugs are decreases, whereas all other classes of populations, that is infected human, recovered human, infected water bug, are all increasing. Even the water contamination level is found to increase. Next, optimal solutions when all control measures are implemented, that is U1, U2, U3 not equal to 0. The solutions of the optimal control system has been obtained when 3 intervention strategy such as health education and use of protective cloth U1, use of insecticide spray U2 and reductions of water contaminations U3 are applied. It was observed that the from figure 4a to 4a, the infected human populations age and the populations of the total water bugs, that is susceptible water bug and infected water bug, are both decreases. However, the number of susceptible human SH and recovered human RH are both increasing. In this case, the water contamination is also decreasing with time. Control profile of 3 strategies. The control profile of strategy 1, which is health education and use of protective clothing, and strategy 2, which is use of insecticide spray, are plotted in figure 5a to 5b respectively. The monotonic decreasing curve corresponding to these 2 control strategy imply that the optimal control efforts needed for controlling the disease are decreasing. On the other hand, the profile corresponding to the control strategy 3, which is for the reductions of water contaminations, is initially increasing. And last section's conclusions. Here we conclude that there are 2 equilibrium points: Bully ulcer free equilibrium point and second Bully ulcer present equilibrium point. The stability analysis results demonstrate that the Bully ulcer model is locally asymptotically stable when kernel less than 1 and unstable. The analysis reveals the existence of forward transcritical bifurcations about the critical value are not equal to 1. This study represents an optimal control of a Bully ulcer model using 3 intervention strategies: health education and protective clothing, insecticides against water bugs, and water contamination reductions. We observe that the situation is out of control when no control strategy is implemented. The situations becomes under control when 3 control measures are implemented. It is also clear that control needed for controlling the disease are decreasing with time. And finally, we conclude that in order to reduce or eliminate this debilitating disease in the population, the government should pay emphasis on promoting the following preventive measures, such as teaching health education to the people, supplying protective clothing, providing insecticides to kill the aquatic bugs, and prohibiting people for no contaminations of water. And here it is references. Thank you, respectable audience, for patiently listening to my presentation. And I also forget my designation. My name is Dr. Sarojit Maji, Senior Research Philomath from Agriculture and Ecological Research Unit, Indian Statistical Institute, Kolkata, headquarter, West Bengal, India. This is my designation and address. Thank you very much to respectable all seniors and juniors. Thank you.
Thank you so much, Dr. Smarajit Maji. Are there any questions from the audience? Doctor, I do have a question, and I would like you to please answer me, because this is all new to us, like exactly like you mentioned. Yes. We are in different hemispheres, and there are several different hours, and the subject we're presenting is very interesting. I'm interested in knowing if those 3 measures that you said that needs to be applied to have optimal control, are they applying in your country or in your research area?
Yes. Yes, ma'am. Yes. Hello?
Doctor. Yes, you mentioned that you needed like 3 measures, measurements to have an optimal control.
Yes.
Is it of your knowledge that those 3 measurements are being applied back in your country?
Actually, this field is Nigeria. Okay. In our country, India, and its adjoining countries like Bangladesh, arsenic concentrations in groundwater and surface water is higher in the adjoining Gangetic plains and deltas, similar to the African environment. And this may lead to an increase in the prevalence of bully ulcers in India too in the near future, thus creating a great burden on our social and economic aspects of our health system. And in the following sections of my article, a brief review of the epidemiology of the disease bully ulcers in African countries is presented. This is the main concern of my study, so that this concept may be used in the future for the prevention of this disease in India. And this is the this is not this is a model-based theoretical study. Okay. And yes, real data from areas where the disease bully ulcers exist can be used to effectively estimate the parameters used in each of the models. The actual data will intensify the research on the bully ulcers. The genuine data can explore the global burden of the disease and its epidemiology, which is not well understood. Okay, madam.
Yes, thank you.
This is only model-based theoretical study.
Yes, thank you so much again for your presentation. It's very much appreciated, and the subject is very interesting. I think the Buruli ulcer is, like you said, like a very harsh disease, and we need to stop it.
We are the first author to work in this research field in India. We are the first author.
Can you repeat?
Sound is not clear.
It's okay. Is it okay if we end your presentation now?
Okay, thank you. Thank you.
Thank you so much. Have a nice day.
Thank you, ma'am. Have a nice day. Thank you, madam. Thank you. Namaskar.
Thank you. Bueno, continuamos. Entonces, vamos a dar paso ahora a la presentación del doctor Jorge Torres Gómez de la Universidad Técnica de Berlín con su tema que se titula Aplicación de las matemáticas a la nanomedicina. Buenos días, doctor. Bienvenido.
Bueno, muchas gracias. No sé si continuar. Maybe I might continue in English. So Samaraji may follow the slides. Okay. Then let's try.
Yo les recomiendo que sea según como tenga usted estructurado su presentación.
Then we follow in English, and then Samari might participate also. Just a matter of inclusiveness, you know.
Yeah, thank you.
It's a joke. Yeah, can you see the slides?
Yes.
Yes, the full version, that is full screen. Okay, wonderful. So welcome all to this talk. I'm really happy to be here with you. I do hope to meet you soon in Mexico, maybe not this year, but maybe the next year, and to meet on site. And wonderful idea to have this event and to have the opportunity to share ideas with this, let's say, mathematical department at your university. Then the topic we are trying to address today is concerning the applicability of mathematics in the nanomedicine. I will be much more descriptive. That is, in contrast to previous presenter, I will not introduce too many mathematical equations. Sorry for that, because this is a mathematical forum. But if any, please let me know, and we can go into much more details. I'm currently working in the School of Electrical Engineering and Computer Science in TU Berlin. My major is regarding electrical engineering, specifically telecommunication networks. And then the topic that I bring today is concerning how do we communicate in nanomedicine applications using molecules. No? Okay. Then, as a summary, let's have a brief introduction to molecular communication, and then let me point out to some couple of research directions that might be in the interest of the community. One is concerning this timely sensing for in-body application here. And the second one that is raising a lot of concern is concerning expandability method for the machine learning models, and especially used in molecular communication scenarios. So let's bring some applicability just to follow how what is this about. If we consider in healthcare application, precision medicine application also, then probably comes to our mind such a scenario like this one. That is, these are some veins with some capillaries, and then probably inside we might find some tumor that where we want to provide some specific treatment. And then the current method that we have is just to target all possible vessels, all possible capillaries in the system. And then if there is a tumor, then we are lucky. But if there is not a tumor, then we might introduce some harmful treatment to those sections where the tumor is not located. And then precision medicine is based on targeting specifically the region that we want to target, specifically this tumor that we have here. Then one solution in mind is to use nanosensor technologies, and then to use the nanosensor to carry the drugs to deliver specifically there, and not to deliver in any other region inside the capillary system. And then the application works in this way. That is, we include or we inject some nanosensor in the blood flow, and then this nanosensor by some means will be able to localize, self-localize their position inside the vessel, and in somehow will be able also to localize the target. That is, to detect that something is happening there, and when being there, then they release the drug. This happens here in this case. That is, if we envision the nanosensor as really teeny machines that may travel with the blood flow and may carry some drugs, then they can timely deliver these drugs in the tissue, specifically in the tissue, in the target tissue where the disease is located. Then assumptions concerning this nanosensor in the current literature, like this paper, for instance, is that these nanosensors are comprised of a navigator, that is, they are aware of the location inside the human body. They also may steer their direction to left to right, to up to bottom. They also have some information molecules, or may have some drugs to deliver here, may have information molecules to communicate with other nanosensors or to communicate with other items inside the body. There is also some fuel just to have some energy resources to move or to actuate or to sensor inside. And this is optional. We might have a propeller also, that is to steer also the nanosensor. Just a little bit of history concerning to arts. If you have the opportunity to travel to Germany and then you visit this museum in Dresden, this is the Museum of Art, then you might find this nice piece here. And this is referred to a small chair. And then in the surface of this chair, we have many faces scarred. We might point in history that this is the very first time when nanotechnology applies. That is, we are talking about the 16th century, just to put in the surface of this teeny item something like 300 faces is something really amazing at that time. This is something you might get amazed because it's quite difficult. Then looking back to history, if we are talking about nanotechnologies for the very first time, at least here in Germany, then I think we can go to the 16th century here. Then talking much more specifically, let's consider what we are talking about when we specify this biological networking and also the physical component to bring an overview on the items that we are using. That is, if we go to the left on this scale, we have the meter in distances in the human scale. For instance, our size, my case, 1 meter and something, I'm really short, let's say, but we have also this Mount Everest big distances. And also, if we are quite curious, there is this Carl Sagan exobiology theory. There is a nice video we can follow where they imagine or they envision some huge bodies in places where the impact of gravity is really low. But this is just coming from imagination. On our scales, we are in this case. That is, we are considering the cellular scale, and then we are playing in the size of bacteria, we are playing in the size of viruses, in proteins, in DNA, but also using molecules and also using atoms to communicate really nano devices between each other. And if we compare with the current CMOS technology, we are more or less in this size, in the nanofiber size, maybe in the CMOS technology for the nano devices, or in the nanotube technology when considering this emission of molecules. Specifically, what we are targeting is a scenario like this one. We have a transmitter nanosensor, we have a receiver nanosensor. We are talking of distances between 100 nanometer and 100 micrometer in the size of the bacteria, or even in the size of DNA or protein or viruses distances. And then from there, the transmitter may try to use molecules to emit information, to emit the zeros and the one. It can be used in the way that we modify some properties of the molecule itself, and then this property might be somehow read at the receiver side. By reading this property, then we can decode. If this is a 1, if this is a 0, we will give an example on the next slide. But what is happening here, in addition, is that when the transmitter releases the molecules, then these molecules start to diffuse to the receiver. Meaning that some of them may get the receiver, but some of them not. And this is quite challenging to describe. In terms of network performance, in terms of communication performance, in terms of directivity from the transmitter to the receiver, imagine also that we are in the blood vessels. It means that this molecule may travel from left to right because of the blood flow, drifted by the blood flow, but might also include some turbulences inside and so on, which is quite challenging, and this is where mathematics plays a big role in this case. If we consider in more details what is happening when we consider molecules diffusion from the point of view of communication, let's assume that we have here a transmitter in this point, and this is a point release that magically start releasing molecules. This is a model, and let's assume that we have a receiver concerning this circumference here, meaning that the receiver will detect whatever molecules may get into an area that we have. And if we do this experiment according to diffusion, then when we release molecules, they will not travel directly to the receiver. And this is quite challenging. Yeah? Then what happens that we will have a lot of uncertainty when trying to describe this process of emission, recession using molecules. We will have a lot of interference, intersymbol interference effect. This is something that we can discuss on details later. And we will have a lot of delay, but not a deterministic one. We will have an stochastic one, because the molecules will wander around before the destination. Then in these highlighted areas is where the molecules spend most of the time. Then it means that the molecules spend some time here, and then there, and then there, and finally get there. And this is happening for one single molecule. But if we have many, this is something that will happen with a lot of randomness. Just to provide an example, let's try to open this video. Let me stop this last point that I have here. Yeah. And then this is a video where we might visualize what is diffusion talking about. That is, this is something that we know from the high school mainly. If we release some drop of some element here, then the individual molecules will start to diffuse inside this bottle. Then this is what is the process about. That is, we release one drop of dye, and then this dye start to diffuse all around, and this is the scene that we are facing. We have a lot of description concerning this. Is related to this mathematics size that we have from classical mechanics, but mainly from the Einstein formulation. And this diffusion, if we want to understand what is happening in the nanoscale, is because of the many collisions of this dye molecule coming from this dye with the water molecules that we have in the environment. And because of this many collisions is that this diffusion is happening. From the classical mechanics, something weird happens. That is, if we follow classical mechanics, the speed of one single molecule of this dye will go to this speed, 13 meters per second. It means that if we release one dye molecule in one corner of our room, it will go in less than 1 second to the second corner, which is not true in practice. This is not happening in the real world. Then Einstein came with this formulation where instead he analyzed the many interactions that the particles will have with the main one, that is displacement, and then he considered the problem from a probabilistic point of view. Then he came with this differential equation, second-order differential equation based on time, based on the position of the particle, with a new constant that is referred to the diffusion coefficient of the particle, which is quite important to describe how this process will happen. It will take 14 hours to move. And this is what is happening in the real life. If we go a little bit further, let me go to the next slide. Okay, yeah. Then this process has been a lot of time discussed in the literature. Came firstly from Robert Brown, who analyzed this Brownian motion because he was looking with some particles that were in the surface of water, and they were magically moving without the impact of wind, without the impact of any other external forces. And then he was thinking, maybe these particles are alive, because this was particle coming from plants. But then Adolf Higgs introduced, let's say, a major milestone in describing what is happening here. And then Adolf Higgs, for the first time, introduced this second-order differential equation, analyzing what is the concentration level of molecules regarding time and regarding position, including this diffusion coefficient here. And then later on, the ones who describe indeed what is happening concerning the physics behind is Albert Einstein. And then magically, he came with an equation that is quite similar to the Adolf Higgs. That is, they are two the same equation except for the variables that we have. And then Einstein lets to interpret this concentration level when coming to one single particle might be interpreted as the probability for the particle to reach some destination. This is just out of curiosity a little bit. Then how do we use these molecules to emit information? That is, let's assume that we want to emit the sequence of 1 and 0s, and then we use what we call in communication environment, what we call as a modulator. And then let's assume that we want the carriers of molecules, and then we want to emit in these carriers this amount of 1 and 0s, this sequence of 1 and 0s that we want to have. Then the easiest way to do so is just to say, whenever we have a 1, then let's release molecules. This is what is happening on the channel. Whenever we have a 1 on the sequence, then we release molecules. Whenever it's happening a 0, then we do not release any. And this is a way to encode information into the amount of molecules in the channel. And then on the receiver side, we might count. If we receive a huge amount of molecules, then we might interpret, the emitter is emitting a 1. If we do not receive any or little, then we might say the emitter is not sending a 1, it's sending a 0. This is one way. Even we can scale the order to emit even much more molecules, and then to encode not a single one, but a sequence, a 1 and 0, into one single emission. Then we can save bandwidth, we can save resources on the emitter side, and then to speed the communication rate. Specifically, if we analyze this as a big picture, we will have a chain like this one with mainly three different blocks. We will have the transmitter, we will have the physical channel, and then we will have the receiver. And then on the transmitter side, we will have the encoding and the part production release mechanism. This is what is happening here. And you can imagine that it's not the same like releasing in a single point many molecules than releasing by these gates as happens in a cell typically. That is, the description is quite different. Doesn't happen the same if we have this emitter mechanism that is quite close to an sprayer. Then in this case, we have an initial speed of molecules in one preferred direction. Then you can imagine what we might describe here is the side. But if we go to the channel, even worse. That is, we might assume only diffusion happens, but also chemical interaction with other molecules might happen. And then we need to include in this big equation, not only the case of diffusion, but also degradation. There is some particle may get broken or may get transformed into another particle, and the new particle might not be detected by the receiver. This is something to take into account. Might happen drift because we are in the vessels. This is one additional thing to include also in the equation from physics. But might happen also this very non-linear effect related to turbulences might happen. And in this case, this is quite hard to describe what is happening between the emitter and the receiver. On this block, concerning the receiver side, is quite dependent also on the geometry. If we increase the radius, if we decrease the radius, if this is not spherical, if this is like a cube, then the probability for the particle to get the same. And in this case, it's quite challenging also to describe what is happening between emitter and receiver. Specifically, this was more or less on topic. This is a quite amazing topic from the communication perspective, because this is a metric that provides how age we are at the receiver side here concerning the status of the emitter. And this finds a lot of applicability when we try to know in the receiver what is happening here. And then we want to be at the receiver as most updated as possible. Then we need to provide a metric how age or how fresh we are on the receiver concerning the emitter side. Let's consider this example. Let's release one single particle at the emitter, and then he travels by diffusion to the receiver side. Then if we measure in a plot what is happening regarding the time evolution of the particle when traveling from the receiver to the emitter, each of the particle itself increases linearly with time. Then when this particle gets the receiver here at D1 prima, then their age on the receiver side start to account. Yeah? That is, in this curve, in this linear description, then we have the age concerning the emitter at the receiver side. Because we are not